In this section, we're going to develop a theorem about how to find the derivative of an inverse function. Now, this will apply for any sorts of functions that have inverses, including but not limited to the relationship between trigonometric and inverse trigonometric functions, any function with its own inverse, as well as derivatives of eventually exponential and logarithmic functions. So as we're getting started, first thing I want to remind everybody is what is the definition of an inverse function. So if a function is one-to-one, then there exists an inverse function for it that reverses the roles of the inputs and the outputs of the function. So if x is the input to the inverse function, that would be the output of the original function. Vice versa, if it's the output of the inverse function, it would be the input to the original function. So other things, the domain of f inverse is going to be equal to the range of f. This is due to the fact that, once again, inputs and outputs are flip-flopped. In addition, the domain of f is going to be equal to the range of f inverse. Now, both of these situations could involve a domain restriction that makes one of these functions into a one-to-one function. So the graph of y equals f inverse of x is the reflection of the graph of f. Graph of y equals f of x through the line y equals x. So just to give you an idea of what that could potentially look like, I'm going to draw this over here because we're going to do some theorems about it. Let's draw just a squaring function, but only the right half of it over here. If I were to draw in the line y equals x, then corresponding to all of these points, there will be a point directly through here. It looks something like this. So for every point that's over here, there's going to be a point the same distance away directly through that line. If we refer to this point up here as AB, then this point down here would be the ordered pair BA. Now, the big question becomes, how are the slopes of the tangent lines going to be related to each other at those 2 points? So with that in mind, let's say that we're dealing with y equals f inverse of x. What I'm going to do is apply the definition that I gave above and say that this means that f of y is going to be equal to x. Next, I'm going to use the technique of implicit differentiation to differentiate both sides with respect to x. So derivative with respect to x of f of y is equal to the derivative with respect to x of x. Now, according to implicit differentiation, this means that this would be f prime of y times the derivative of the inside with respect to x. This is equal to 1. Now, ultimately, though, we're trying to get dy dx because that's what the original inverse function was. So dy dx is going to be equal to the reciprocal of f prime of y. Now, y, of course, was equal to the inverse function of x, so another way that this can be notated is that this would be 1 over the derivative of f evaluated at f inverse of x. So let's put that into perspective of what we have over here on our graph. What that means is that the slope of the tangent line that is right here and the slope of the tangent line that's right here would be reciprocals of each other. You'll notice that this one is very large and positive and that this one is very small and positive. So the slope over here will assume that this function over here is y equals f of x and that this one down here is y equals f inverse of x. So this slope would be equal to f prime of a, and this slope down here would be equal to f inverse prime, that's not very good notation, is it? Evaluated at b. So I guess the better way to say that is this would be the reciprocal of f prime of a, except we're not allowed to say a because that's the y value, so this would be f inverse of b. So that's what this formula is trying to convey.